technique part 2. Part 2, this is what we're going to cover today. Well, what we have covered yesterday is the review on the step response of underdamped second order system. Okay, and then also vector representations. Okay, so we have talked about defining the root locus, properties. Okay, and lastly we talk about sketching the root locus. So today what we're going to cover mainly, we're going to do some review of sketching root locus and then refining the sketch. Okay, so summarizing from what we have learned yesterday. All right, so remember the first lecture, if you look at chapter 8 in the textbook, okay, we talk about OptiTrack camera tracking system. Okay, so this is the OptiTrack camera tracking system. Okay, so the block diagram of the camera is this is the closed loop block diagram of the camera, and this is the open loop closed loop transfer function. Okay, by now you should be familiar with the closed loop and open loop transfer function. Okay, so there are two ways how we're going to design the gain here. Okay, there are two ways. So the first way is the first option that is covered in the introduction of chapter 8 is where we're gonna find the closed loop transfer function, and then we're gonna create table 8.1. Okay, create table 8.1 where we're gonna do one by one. K equals to 0, K equals to 5, 10, 15, 20, 25, 30, and we're going to find the poles. The poles, which is the poles here. Okay, we need to find the poles here. So what happens if K is 0? So we're going to get minus 10, 0, and then what happens if K is 5, and then K10, K15, K20, blah, 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 blah. And then next we plot it in the S-plane. Okay, so this is all the plot from table 8.1. Okay, and then finally we find the root locus. We find the how is the poles moving up here, and how is this one from the poles from negative 10, how does it move as the gain increase to 50? As the gain increase to 50, how does it move to here? So it will be minus 10, blah, 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 minus 5, and then it will go up. Sorry, it will go up. Okay, so another one, minus 10, 0, and then it will go here, minus 5, and then it will go down. Okay. Alternatively, another option to do this, okay, is using root locus technique. Okay, using root locus technique. So by using root locus techniques, we eliminate the lengthy table 8.1 that we have to do the table, and we have to estimate the gain K, K0, K5, K10, and do the computation. Okay. So in root locus techniques, there are two major steps, which is sketch and refine. What we have learned yesterday is sketch. Okay. In sketch, what we have learned yesterday, there are 5 rules. So the root locus techniques can also arrive to this root locus. Okay. Except that there is a techniques for it. Okay. So in whatever way, we can do option 1 or we can do option 2. But for this chapter 8, we learn the techniques, the smarter way to do it. Okay, so less mathematical computation. Okay. So what are the 5 rules of the root locus techniques? This one we have covered yesterday. Okay. The first one is the number of branches. Okay. Looking again at this result, this is the result from the OptiTrack camera. Okay. So initially when K is 0, we have 2 poles at 0 and minus 10, right? So we know that as we move on, as the K is increases from 0 and it increases to 25 and it increases to 50, so the poles is moving, going up and going down. So from these results, you see that there are 2 branches. The first branches is from the poles of minus 10. The second branch is generated from the poles of 0. Okay, so the rule number 1 of root locus says that it's about the number of branches. The number of branches of the root locus equals the number of closed loop poles. So from these two branches, we know that there are two closed loop poles. There are two branch which present the two closed loop poles. Okay. So also symmetry. Okay. So the root locus, the rules of the locus, and it has to be symmetrical about the real axis. If you look here, this is the real axis. Nampak tak ni? This is the real axis. So we have the upper part and lower part. So it is symmetrical, but then it goes to minus 10, it goes up, and symmetrically 10, 0, it goes down. So it has to be symmetrical. Okay. The rule number 3, the real axis segment. On the real axis, for k more than 0, the root locus exists to the left of an odd number of real axis, finite open loop poles or finite open loop zeros. What it says here, as the k is increasing, okay, so the root locus exists to the left or this side of the real axis. Okay, so now rule number 4, the starting is about the starting and ending point. Okay, the starting of the branch, the locus here, must be from poles. Okay, must be from poles, and it must end at zeros. So here it must be from poles and it must end at zeros. But in this result, there is no zeros, right? But actually, as the poles, as the branch locus is moving up, actually it is moving to a zeros here, which is, we call it infinite zeros, somewhere in the space here. Infinite zeros. Okay. Similarly, as for pole 0, it will move to the poles when k is 0. It will move somewhere down. It is actually moving to a zeros, but it is somewhere in the infinite space. Okay. So lastly, the rule 5, behavior at infinity. But the question is, when it goes to infinite, how is the behavior? Where is it going? Is it diverging to the left, or is it to the right, or is it going up? So this is where we use rule number 5, where we find the asymptote. So those are the things that we have learned yesterday, is summarized in these two slides. Okay, next is, okay, example. Catching a root locus with asymptotes. Okay, for example, for this one, catch the root locus for the system shown. So this is in example 8.2. Okay, if you have the textbook with you or the PDF copy, right? So first thing is we identify the zeros and poles. Okay, so for this one, the zeros is, what is the zeros? What is the zeros for this one?
-3.
Okay, so the zeros is, the zeros is -3, right? So kita terus draw. Okay, we make it here -1, -2, and -3, and -4. So the zeros is at -3. So what are the poles?
-1, -2, -4.
-1, 0, 0, -1, -2, and -4.
-4.
Okay. So you know that the rule says the poles has to go to zeros, but there is only 1 0. Okay, there is only 1 0, but there are 4 poles. Empat orang senang macam ni lah. Four men nak usah seorang awet. Itu the concept dia. Okay, but it's not nice to record it here. Okay, but those are the concept. Okay, now, so how do we know which one is chasing for this one? Okay, we know that generally the rules is this one will go somewhere here, this one will go here. The poles here will be attracted to the nearest zeros. This one here will go somewhere. Okay. But the question is how is the pattern shape of the pole that we need to do the asymptote. So for the asymptote, the real part, what do we get for the real part? We will get -1, -2, -4, minus with -3 over the number of poles, which is 4, minus the number of zeros, which is 1, which is equals to -4/3. And the theta will be, the angle will be 2k plus 1 times with pi over the number of poles, 4, minus the number of zeros, 1. So for k equals to zeros, you will get pi over 3. Okay. For k equals to 1, you will get pi. For k equals to 2, you will get 5 pi over 3. Right? So it will be somewhere minus 4 over 3. So somewhere around, probably around here. Pada tak? Minus 4 over 3. And the angle will be somewhere here. 1. Okay. Ini kita dah cover yesterday. Okay. Somewhere here. And somewhere here. And somewhere here. So this one is pi over 3. Pi and 5 pi over 3. Okay, right? So the question is, so we know that the root will go somewhere like this, and one of the root will go somewhere like this. Okay, somewhere like this because it will cross somewhere here. Okay, all right. So from this sketch, this one, okay, kita bawa ke sini. So we know that this one, these rules, for the sketch, it meets the 5 rules. The number, how many number of branches kat sini? It has 1 branch, 1, 2, 3, and 4. 4 branches. Okay, ada 4 branches which represents the number of closed loop poles here. Okay, so which is 1 as was the s to the power of 4, this closed loop poles. Okay, so symmetrical. So you see that this one is symmetrical between up here, between up and down. It is symmetrical. Right? And then real axis segment. On the real axis, for k more than 0, the root locus exists to the left of an odd number of reals, finite open loop poles, and or finite open loop zeros. So you see here that this one is moving to here, finite open loop poles, finite open loop zeros. Okay, and this one is moving somewhere here to the zeros here. Okay, and this one is also moving somewhere here. It's finding the zeros around here, and this one is also moving somewhere here, finding the zeros around here. So that is rule number 3. So this, for k more than 0, so it's above. So rule number 4, the starting and ending points. So the starting must be from poles to 0. Itu rules. So kalau 0 tak wujud, it must be somewhere at the infinite. So rule number 5 is the asymptote. So you know, you already calculate the asymptote. So this is the asymptote. Okay, so those are the sketching. Okay, now we are ready for the next point, which is refining. Okay, what is refining? First thing is, okay, this one, the root is moving here. But what point is this? What is the point here? Okay, and at this point, what is k? Those are the things that we are going to cover for today. Okay, so when we refine the root locus, there are 3 areas. First is the real axis breakaway and breaking points. Second is to find the j omega axis crossing. And third is angle of departures and angle of arrival. Okay. So the one that is the first and the third is usually we're going to do some simulation, and but for the second one, we are expected to know how to find the j omega axis crossing. Okay, so what is j omega axis crossing? Back to the previous slide. The point here that is crossing here, this is we call the roots that crossing the j imaginary j omega crossing. This is what we call the j omega crossing. So the one that is crossing this imaginary part, because okay, this part, as the root around this part, it means that the system is stable. This part is marginally stable, and this area means that the system is unstable. So our task is we need to make sure our k is in the, as we increase the k, it has to be in the stable region. Okay, let's look one by one. Okay, first the breakaway and breaking points. I just simply take from the example 8.3. Okay, what is breakaway and what is breaking point? That's the first thing that we need to know. Okay, Find the breakaway and break-in points for the root locus of figure 8.13 using differential equation. For example, we have this root locus. We know there are two poles here and two zeros. You know that the poles will be attracted to zeros. So these two poles will be going towards each other, but then repel. One will go into the zeros, another one will go into zeros 5 here. The question is, at what point here? The question is, at what point here? And at what point here that it starts to break away? At what point here that it starts to break away? And at what point here that it starts to break in? Okay, so those are the break-in points and break-away. So, okay. Again, saya lukis balik. So, breakaway. What is the breakaway point and what is the break-in point? Okay. So, there are three methods to find the breakaway point and break-in point. The two methods are using mathematical equations. Okay, so the first method is differentiation. We can differentiate. So what we differentiate, so the solution is here. Using the open loop poles and zeros, we represent the open loop system where root locus is shown in figure 8.3 as this one, KGH. So it means that this transfer function, okay, this forward function, we differentiate it. Kita selesaikan, we do like this and then we differentiate this forward function, okay? And then when after you have differentiate and then you can solve for K and then we differentiate the K, sorry. So you, you multiply and then you get this one and then you able to differentiate. So this one is using the rules of differentiation for a partial fraction, okay? So when they differentiate and then when you are able to find the value of the real parts here, which is minus 1.55 and 3.82, okay, which is the breakaway and break-in point, okay? So in this case, this is minus 1.45 and the break-in point is 3.82. Okay, so one way to find the breakaway break-in points is using differentiation. Another part is without, we can also do it without differentiation. Okay, so without differentiations, we just have to use equation 8.37, which we can look at the textbook. Okay, and we come up with equation 8.38 here. Lepas tu kita simplify dia. Then you are able to get the same answer, which is breakaway points here and break-in points. Breakaway and okay. So another method is we can use the MATLAB. Okay, we can use the root locus program, which is as discussed in H.2. Okay, so from the root locus program, you can pursue this one. It's just that for your awareness to know that, okay. So the results of finding that, use the program to find the breakaway and the break-in point. So the point for number 3 is we can use actually MATLAB. So I'm going to fast this because I don't expect the mathematical parts, the tools on mathematical parts that you need to cover. Okay, but we will do it in MATLAB later on. Okay, the second one. For the sketching, for the refining the root locus, the second method is finding the J omega axis crossing. Okay, what is the J omega axis crossing? It is this point here. Okay, so it is this point, but since we know that for the root locus, it is symmetrical, the point here is always symmetrical to this point, to the real part. So as long as we get this point, we know we are always able to get this point. So this is the J omega axis crossing. Any questions so far? Any question?
No, ma'am.
Okay. Alright, so can I proceed? Okay, so for example, this block diagram, feedback system. So this is the root locus. Okay. So how do we find the J omega axis crossing? Okay, so you can look at example 8.5 here. Okay, so for this example, okay, when we how to find the J omega axis crossing is using the first step is we have to find the closed loop transfer function. Okay. So we have to find the closed loop transfer function for this system. So in this case, the closed loop transfer function is equals to D over 1 plus G. Okay. So using this, then you are able to get this closed loop transfer function. So once you get this, then we use the root Hurwitz that we learned in chapter 6. Okay, because root Hurwitz is to find the stability. So using the root Hurwitz, we are able to come up with tables. So in this case, it is s to the power of 4. Kan? So we're going to start with s4 and then moving down to s to the power of 0. And then kita masukkan the value 1, 7, okay, 14, 8 plus k and 3k. And then we find the determinant here. Right? C1. So C1 is the determinant. So by now you all dah tahu kan nak cari the root locus. The root Hurwitz 1, 7, 14, 8 plus k over 7. Am I right? Okay. So that is C1 and this is C2. So what is C2? C2 will be minus 1, 7, 3k over 7. Okay, and then the CD, then we are able to find D1. So what is D1? Sorry, makin lama makin atas pula. Okay, so D1 is minus 7, 90 over K, serta 8 plus K, 21K over 90 over K. Okay, so this is, then you get your D1. Okay, so D2 tak ada, and then E1. What is E1? So your E1, kat sini So your E1 will be all the value dekat atas ni, 90 over K minus, and then this one is D1 plus 2, 21K, 0 over D1. So you dapat your E1 equals to 21. So when you have done that, what we need to do, okay, a complete row of zeros gives the possibility for imaginary axis roots. Okay, so your chapter 6 must be strong. Okay, in chapter 6 kita tahu that if we have a complete rows of zeros, okay, gives the possibility of imaginary axis. So we are getting a complete rows of zeros. Okay, so for positive value of gain, those for which the root locus is obstructed, only S1 row can now give a complete of zeros. So they are looking at S1 here. Kalau kita dapat dia complete rows of zeros, okay, then kita akan that means that in the root locus it is actually crossing the J omega. Okay, so you can look back at the theory chapter 6. Okay, so in this case dia assume this one is equal to 0, so it akan jadi minus K squared minus 65K plus 720 equals to 0. Okay, so daripada sini you are able to find your K equals to 9.65. Okay, so from this K equals to 9.65. Okay, forming the even polynomial. So you know that kita letak this one zeros and we cut this one zeros, right? So cuba you letakkan value 9.65 dekat dalam ni, then you should get 0. Can someone try to do it sekejap? Minus 9.5 squared minus 5, 9.5 plus 720 over 90 minus 9.5. You get 0. Dapat tak 0? Did you get 0? Anyone?
Negative 0.00.
Okay, so 0 lah tu. Kan? Kita tak thank you. Siapa tu? Who is that?
Sabrina.
Sabrina. Thank you, Sabrina. Okay, so you get 0, right? So, kita lepas ni 0, then we look at up here as to the power of 2. Okay, then kita letak dia punya forming the even polynomial with 9k 9.65, then dia akan dapat macam ni. Okay, so it means that 90, ambil yang ni. Okay, and we bring it down here. Then dia akan dapat 90 minus k s squared plus 21k. So, masukkan nilai k and then you get 80.35 s to the power of 2 plus 12 or 2.7. So, daripada sini, you will get your s here. Your s is found to be equal to j plus minus j 1.59. So, thus the root locus crosses the j omega crossing at 1.59. So, actually the value here is j 1.59. Okay, nampak ni plus minus ni. Okay, so it means that here is j minus j 1.59. And at j 1.59, how we the gain k is 9.65. At this one, the k is equal to 9. Okay, so what can we conclude? We conclude that the system is stable for k from 0 to 9.65. Okay, so the system stable from k from 0 until 9.65. What happens above 9.65? As k more than 9.65, what happens?
Stable.
The system become unstable. Okay, the system akan jadi unstable. What is k? K ni is, kalau dalam controller, k ni is our gain. So maksudnya kita adjust the gain tu, kita tak boleh adjust lebih daripada 9.65 untuk dalam for this case. For this k ni, we cannot adjust more than 965. The k has to be from 0 to 9.65. Above 9.65, then you will get your output response here, your CT. Apa you get? You will get unstable. But for this one, okay. But for this one, then you are able to get your output response stable. Itu maksudnya. Faham? Any question? Okay, I skip the maths here and I expect you to do it because there is homework for you. So you can stop, try to do the maths. Okay. So we finish the J omega crossing. Okay. And then the third one, in refining sketch, you need to know how to do the angles of departure and arrivals. Okay. So this is angle of departures and this is angle of arrivals. It means the angle of departures is, what is the angle? Let's look here. What is the angle here that it starts to split? Okay, so this is angles of departures. And angle of arrival, what is the angle here? that it starts to collide balik, berjumpa balik. So this is angles of arrival. So far so good? Okay, small?
Okay, ma'am.
Alright. So, okay.
Yes,
So
ma'am.
those are, sorry? Anything?
No, ma'am.
Okay. So I'm not going to cover angles of departures and arrivals, the mathematical parts, because we're going to do it in simulation. But the one that you guys need to exercise on is on this J omega cross. Okay, for the assessment. Okay. So now let's try to do skill assessment 8.4. Okay. So the problem is given a unity feedback system that has the forward transfer function GS equals to K, the gain, some gain, multiplied by the system which is S plus 2 over S squared minus 4S plus 30. Okay, let's try to draw this first. Okay, so what does it mean to have a block diagram which is there is a K here and there is a system here which is S plus 2 over S squared minus 4S plus 13. This is the system and this is the gain. This is the output S and it is a negative feedback to the input, which is R. It's too much. Okay, so a unity feedback, okay, and has the forward transfer function. So all these things are S. Okay, so do the following. Sketch the root locus. So you know now, you tahu macam mana nak sketch, right? See here, sketch. So you have to make sure that you meet the 5 rules. And then find the imaginary axis crossing. So now this one, the B is start to do the refine and then find the gain K at the J omega crossing. And then find the breaking point and then find the angle of departures from the complex. Okay, so let's look one by one. Sketch first. Find the zeros and poles. So in this case, the zeros is 2, very clear. The poles, you need to solve it. So when we solve it, we get a complex pole, a 2 complex poles. This is my network is that. Okay, so 2 complex poles. So this is the root locus, the sketch of the root locus. So you know that, for example, the the poles is 2 plus J3 here, and then 2 minus J3 pole. Okay, and the zeros is set minus 2. So now we tahu that the root locus, the zeros have, the poles has to go to zeros, right? So in this case, look at the root locus here. It goes, one will go here and into these zeros number 2. Another one will go here and it will go somewhere zeros which is at infinite space. Okay. In this example, there is no need to find the asymptotes because we know that we're going to expect that because there is a complex pole, we get a complex pole. Okay, so there is the sketch the root locus. So what is B? Okay, finding the imaginary axis crossings. So for this one, kita kena cari dia punya, first we need to do is we need to first find the closed loop transfer function. So CS here, using this formula. Okay, so this is what we get. And from this closed loop transfer function, then we start to build the truth table. Okay, so the truth table here, since it is s to the power of 2, so kita ada s to the power of 2 here, so we get 1, k minus 40, 40 ke 4 here? Supposed to be 4, okay, 2k plus 13 and 0. So to get s to the power of 0 here, so we use the determinant, E1, right, determinant, E1 which is minus 1, k minus 40, 2k plus 13, 0 over k minus 40. Then you are able to get the C1. So the key for an imaginary axis crossing is we need to get rows of zeros. Okay, the rows of zeros in this case is 2k plus 1, 13. 2k plus 13, C1. Okay, so When you get 2k plus 13, the row of zeros, then you are able to get your k equals to 4. Betul tak? So 2k plus 13 equals to 0. So your k will be 2k plus 13 kot. You need to check again dia punya ni. K will be minus 13 over 2. Macam mana saya tak dapat pula ni? Jawapan dia lain. Okay, tak apa. But your part you can do it. Okay, you try to do it. Okay, so and then bila dia dekat the rows of zeros, then we look at the rows of zeros dia buat this one. Okay, no wonder I didn't get it. Okay, so the rows of zeros is you get that one. K minus 40 equal k minus 40 equals to 0. So your k is 40. Okay, so from this one and then dia tengok dekat up to s to the power of 2 here. And then they come up with this. Okay, s squared plus 2k plus 13 equals to 0. Means that s squared plus 2k plus 13 s ke equals to 0. So your k is 4, s squared plus 8 plus 13 equals to 0. S squared plus 21 equals to 0. So your s squared will be square root of 20. Betul tak? Okay. So that is the square root of 21. So this is what you get. So at k equals to 4 here. So the gain k is equals to 4 and the j omega crossing is at here. Plus minus 21. Square root of 21. Okay. So this is answering for B and for C. Okay. So what is the breaking point? The breaking points and the break angles, angle of departures, then we are going to learn how to use MATLAB to find it. Okay. But you by now you should know, ada ke break away point in this root locus? Do you think ada breakaway points?
No.
Tak ada. Okay. Yang ada only break in points. But they merge and they merge here. So this is break. Only break in point ada. Okay. And also the angle of departures. The angle of departures actually tak ada. It is the angle of arrival. Okay. We're going to go to that later on. Okay. Another one, skill assessment example, exercise 8.5. Okay, so given the unity feedback system that has the forward transfer function, Gs equals to K, S minus 2, S minus 4 over S squared plus 6S plus 25. Okay, first sketch the root locus. Before that, sorry, let us conclude this one first, okay? So K equals to 4. So it means that for this system, the gain K here, you can only varies from 0 to 4. Okay. Above 4, the system, your output here will become unstable. Your output will become unstable. If K is above 4. Itu maksudnya. Okay. Tak ada soalan Any question? Before we move to skill assessment exercise 8.5?
No.
No, okay. Alright, so now sketch the root locus for this one. Find the imaginary axis crossings, find the gain K at the imaginary axis crossings, find the breaking point, find the point where the root locus crosses 0.5 damping ratio line. So kita ingat lagi, chapter 4, we learn about 0.5 damping ratio. Okay, find the gain at the point where the root locus crosses the 0.5 damping ratio line. And then you need to find the range of gain K for which the system is stable. Okay, so let's move one by one. Okay, so sketch the root locus. For this one, we have the sketch of root locus like this. Okay, the sketch of root locus, you are expected to do it using hand sketch. Okay, and also my following discussion, I use MATLAB. Okay, so using MATLAB, okay, I put the, you see here in the MATLAB script. Okay, I use put it in the MATLAB script here. The numerator num g equals to polynomial 24, denominator 1625, and then g, which is the transfer function, numerator, denominator, and then r locus g, because we want to create the root locus. Okay, so r locus g, then it will produce this r locus g, and then z equals to 0.5. It means that the damping ratio z here equals to 0.5, and then the grid s grid z0. So we're going to have the grid here. Okay, so for the root locus here, for b, the J omega crossing, kita dah tahu that the J omega crossings is where it is the root locus pass through the imaginary point. Apa itu? The J omega imaginary part. Okay. So before that, this is the sketch of the root locus. We have two zeros here and one pole. So the poles here is moving to zeros. Betul tak? Okay. So the poles is moving to zeros. So in this case, it's very straightforward because there are two poles and two zeros. So one pole we go here and one pole we go here to this one. So if you see here, this one pole, dia akan masuk ke sini and then it will go to the zeros, and the green one pole in the green locus here, it will go to this zero. Okay. So using the MATLAB, okay, we can find that the gain K, the gain K is 1.01. Okay, the gain K here, okay, is 1.01. So as the gain above 1.01, what happened? As the gain above 1.01,
Unstable.
yeah, the system becomes 1.01. So the system becomes unstable. Okay, what is the pole here? What is the point here? That it is 0.013 plus 4.061. So this one is 4.06. Okay, so this one is also, kita tahu yang dia symmetrical, so this is minus J 4.0. Okay, so that is B. So we are able to get the J omega crossings, which is 4.06. And we are able to answer C also. At 4.06 here, the gain K is 1.01. Okay, so this one, so we need to make sure that we control our K here between 0 until 1.01. So which is a very small range when we need to look after. Okay, so next, the break-in point. What is the break-in point? The break-in point is where bila dia breakaway point tak ada dalam kes ni, we only have break-in point here. Break-in point. Okay, so bila break-in point, kita tahu tak ada break-in point. Break-in point, tak ada breakaway point. So the break-in point here, we have the gain K here. At this point, the gain K is equals to 51.3, and the post, the what is it? The line that it goes here, okay, is 2.89 minus 0.0292i. Okay, I here is actually represents Q. So it means that the point, the break-in point is at 2.89 minus K 0.0292. Itu maksud dia. Okay, 2.89 is, so this is the breaking point. So next is the point where the root locus crosses the 0.5 damping ratio. Okay, kalau if you remember, please recall again, okay, because next week we are ready to go to design. So please make sure you revision balik chapter 4, 4, 5, 6, chapter 4 about the transient response. Apa maksud 0.5 damping ratio? 0.5 damping ratio have some meanings in terms of the kind of response. Either it is underdamped, either it is underdamped, or it is undamped, or it is overdamped. Okay, so tengok balik chapter 4. So fikir nak chapter 4. Okay. So in this case, in this one is dia nak the point where the root locus crosses the 0.5 damping ratio. So kita nak tengok root locus ni dekat mana yang cross this damping ratio. So MATLAB can, by using the code tadi tu, dia boleh plotkan di 0.5 line. So we see here the line here that crosses 0.5. Okay. But what is this line? Apa dia? And what is the K here? So this is where kita dapat the line is at minus 2.42 plus 4.18i, and at this part the gain is 0.106. Okay. Okay. So the gain at the point where the root locus crosses the 0.5 damping ratio is 0.106. The point where the root locus crosses the 0.5 damping ratio is at minus 2.42 plus 4.18i. Okay. Any question? Okay. So if we want our system to have the response and under dam response, for example, to have the response under dam, so we know that the damping ratio has to be 0.5. So how much is the gain that we need to set so that we can get this response with damping ratio 0.5? So the gain K that we need to set is at 0.106. Itu maksudnya. Okay. We set the gain K at 0.106. So where is it? Where that we set here? Okay. So lastly, the range of gain K for which the system is stable. So we need to find the range of gain K. Look here, I got three points. Okay. So this is the J omega crossing. You know that at J omega crossing here, the K is 1.02. Okay. Then this one, this part is stable region, and this part is unstable region. Okay. So the gain kat sini 0.346, which is smaller. Okay. Then 1.02, and the gain dekat sini, the gain at the unstable region here for this point is 4.7, which is bigger than the gain at the gain of okay. So what it says is that the range of gain K for which the system is stable is from 0 until 1.02. The range of gain K. Okay. So at this range, the system is stable. Itu maksudnya. Okay, so far so good. So far so good, everyone. Okay, so alright. So this has lots of mathematics. You need to look again at the video or ni. So then I think we are ready for the homework. Okay. So as a homework, as an exercise for you, okay, given a unity feedback system that has the forward transfer function like this, ini macam jawapan je. Okay. Answer the following. Sketch the root locus. Okay. You need to sketch the root locus, and then in your answer, label the J omega axis crossing, breakaway point and break-in point. It asks you to label first. So in your root locus, you need to put an arrow and show which one is breakaway, which one is break-in point. Boleh? Then next is show the steps to obtain the imaginary axis crossings. So what is the steps to obtain the imaginary crossing? So, and then you need to find the gain K at the J omega axis crossing. And then you need to calculate the break-in point. Okay, in this one, it asks you to calculate. So you can look at kita punya break-in points tadi, what method is the best. Whether you want to use differentiation ataupun without differentiation. Okay, but try not to use MATLAB yet. Okay, for this one. This homework is expecting you not to use MATLAB yet. But if you want to verify your answer with MATLAB, it's okay. But the sketch of root locus has to be using your pencil and pen, sketch of the locus for this homework. Okay, And then what is the range of K for which the system is stable? So the range of K, macam ni dapat. Once you get D, then you should be able to write the range of K. Okay. So that is the homework. So that one is